So far we've looked at completing a hypothesis test when we have one proportion and we're comparing it against a claimed value. We've also done a hypothesis test on a sample mean against a claimed value. Now we're going to look at what happens when we have two samples. So there are two samples can either be independent or dependent. And that'll be the first thing that you'll need to determine when you are trying to decide what type of hypothesis test to complete. So an independent sample, the sample values selected from one population aren't related or somehow paired with the sample values selected from another population, so therefore they're independent. And the dependent sample, the values of one sample are related to the values in the other sample. And a lot of times we call these matched pair samples. So let's go through a few examples to see if we can tell which is which. So first example, the list price and the selling price from each of 40 randomly selected homes. So we're looking at 40 homes. We're looking at the list price and the selling price. So these are actually dependent because we are matching the price up to each other with the homes. So they're matched pair. All right, second example, a study of 210 women and 186 men who wore microphones so that the number of words they spoke could be recorded. So if I have to decide whether that's dependent or independent, do the 210 women and the 186 men have anything to do with each other other than their words are being recorded? No. So this is independent. Just because we're measuring the same thing on both populations doesn't mean that they're dependent on each other. A study in which 67 students were weighed in the fall of their freshman year and again in the spring of their freshman year. Okay, again, we are matching those weights against each other, so this is dependent because this would be a matched pair sample. All right, 46 children were treated with low humidity and 46 other children were treated with high humidity. So if I have to decide whether or not that's independent or dependent, just because we're performing two different treatments on two different populations, one does not affect the other, so this is independent. All right, so we're going to compare two population proportions now, and we're going to compare independent samples. So it looks like I put the wrong notes into this slide. I really wanted to talk about the assumptions, so I'm just going to go ahead and talk about them even though they're not here. They should be on your notes. So assumptions are, if we're testing two independent proportions, that the samples are independently obtained using simple random sampling, that n, the sample size, times p hat times q hat is greater than 10 for both sample sets, n1 and n2 denote sample set 1 and sample set 2. Both sample sets are less than 5% of the entire population. And when we're setting up a null and alternative hypothesis for our two population proportion independent samples, our null hypothesis can either be that our proportions are equal, that our two proportions, one is greater than or equal to the second one, or that one is less than or equal to the second one. But you'll notice that all of my null hypotheses have that equals symbol in it somewhere. And then our alternative hypothesis is, depending on which one we chose for the null hypothesis, is either not equals, less than, or greater than. our test statistic is Z in this case, and we find that by taking the difference between our population estimate 1 and 2 and dividing that by the square root of the average of the first and second proportion times the average of the first and second Q values plus 1 over the sample size of n plus 1 over the sample size of our n2, and we take the square root of all that. And then in order to find the average of our proportions, we take the value, our x value from our first population plus the x value from our second population. That's the number of people with the characteristics we are looking for, and we divide that by the sample sizes added together. And then the average of our Q values is 1 minus the average of our P values. And as always, there is a calculator test to run this for you. So let's move on to the example. American Demographics reported the results of a survey on the planning habits of men and women. In response to the question, what is your preferred method of planning and keeping track of meeting appointments and deadlines? The sample results were that 500 men and 500 women participated in the survey. 280 men and 230 women said that they preferred to keep track of appointments in their head. Test the claim that the percentage of men who prefer keeping track of appointments in their heads is larger than the percentage of women. Use a significance level of 0.01. Well, let's take the information that we have from the problem. Our sample size for men was 500. Our sample size for women was also 500. The number of men that we noticed with the characteristic we were looking for was 280. That it would be the number of people who prefer keeping track of appointments in their head. And then of women, it was only 230. So that makes my estimate for my population 0.56 for men and 0.46 for women. So let's set this up. We know that alpha is 0.01, and we need a hypothesis. My null hypothesis is going to be P1. Let's see, test the claim that the percentage of men who prefer keeping track of their appointments in their heads is larger than the percentage of women. So I could do equals P2 or is less than or equals P2. It doesn't matter, either one is fine. And then the alternate hypothesis is that P1 is greater than P2. So if I draw a picture of what that looks like, here's my normal curve. This is going to be a right tail test because my alternative hypothesis is pointing in the direction of my test. And this value up here is 0.01. That's alpha. So I need to find the z-score that goes with that. And z alpha in this case equals 2.33. And if you've forgotten how to do that, it is in the distributions, and you choose normal distribution, area of 0.99, 0, 1. All right, so that is the value that I'm going to be testing my test statistic against. And to find all of the other information I need, I can actually go to stats, over to tests, and then I'm going to scroll down. On mine it's number 6, but it's 2 proportion z-test. How simple is that? And then up comes a table x1, and I'm going to put 500 into that. X1 is not 500, that's n1. X1 is 280. N1 is 500. X2 is 230. N2 is 500. And then I'm going to choose the right tail test, and I'm going to have it calculate it. So the information that I get back is that Z is equal to 3.16 and P is equal to, it's almost 0. It's got 4 zeros in front of it, in front of a 7, so we'll call that 0. And if we look at where that is, it is in my critical region. The z-score is 3.16 is greater than 2.33. That means it's in the critical region. And then my p-value is less than alpha. 0 is less than 0.1, so that's also in the critical region. Therefore, we're going to reject the null hypothesis. Which means that the number of men who prefer keeping track of appointments in their heads appears to be larger than the percentage of women. All right, so that's it for today.